In this example, we would like to estimate the slope of the tangent line to the curve y equal x squared at the point 1, 1. So y equal x squared is just your basic parabola. So the first thing I'm going to do is just sketch the graph of that parabola. So here's the graph of the parabola y equal x squared, and here you see the point 1, 1. Okay. The next thing I want to do is sketch the graph of the tangent line at 1, 1. So here's the graph of the tangent line at x equal 1. And you'll notice that the tangent line is just a line that just touches the graph tangentially at the point 1, 1. So you might be wondering, why can't we just calculate the slope of the tangent line? Well, the problem is we only know one point on the tangent line. We don't know 2 points. And if you recall from algebra, in order to calculate the slope m for a line, we have to calculate the rise over run. But in order to do that, we need 2 points. So the formula was y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are 2 points on the line. So the problem with tangent lines is that we only know 1 point at the line, 1 point on the line. It's the point of tangency. So we're kind of stuck. So what we're going to do instead is we're going to try to estimate the slope of the tangent line using secant lines. So what is a secant line? Well, a secant line is just a line that passes through my function in 2 points. Okay, so for example, I can draw the secant line at 0, 0. Okay, the secant line that goes through 0, 0 and 1, 1. Those are 2 points on my curve. And I can draw the line that goes through those 2 points, and that would be a secant line. Okay, so here you can see the secant line, and I'm going to call the second point here Q0, 0. Okay, so the first 0 is just x is equal to 0, and the second 0 you see is x squared equals 0 squared. And so we like the secant line because I can actually calculate the slope, MPQ, and that is going to be equal to, let's see, 0 minus 1. Okay, that is the change in my y coordinates, 0 minus 1. And I'm going to divide that by the change in my x coordinates, 0 minus 1. So the slope in this case ends up being just positive 1. And although that is not exactly equal to the slope of the tangent line, you can see that they're somewhat close. Both of these lines have positive slope. In order to get a better estimate, what we can do is we can take values of x that are closer to 1. Okay, and then use the secant line at those values. So for example, another choice I can make is I could use x equals 0.5. Okay, and the point corresponding point on the graph is right here. Okay, and now you can see that the secant line that passes through these 2 points, the 2 points right here, this secant line has a slope that is actually closer to the slope of the tangent line. And I can continue this process and I can get closer and closer to 1. I can also take values that are to the right of 1, okay, and use the same process. So let's just summarize what I've done. In order to summarize what I did, I made this table. The first x value I used was 0, and the corresponding point on the graph was 0, 0 squared. And the slope of the secant line was given by 0 minus 1 over 0 minus 1, which was 1. So the first secant line that we were using for our estimate had slope 1. The next thing I did was I used x equals 0.5, and that gives me the point 0.5, and x squared in this case is 0.25. So the slope of the secant line in that case was 0.25 minus 1 over 0.5 minus 1, which was 1.5. So that second secant line had a slope of 1.5. I can keep going. I can use the x value 0.9, which is very close to 1. The corresponding point will be 0.9 and 0.81. And the slope of that secant line will be equal to 1.9. And I can keep going, and I can use 0.99. And I'm going to leave out all the calculations. They're the same. But you will find that the slope of the secant line is 1.99. So if you look at these values, you can see that as I get closer and closer, as my x values get closer and closer to 1, you can see that the slopes, MPQ, are getting closer and closer, so they're approaching 2. Okay, so it appears, if I go back to the original picture, it appears that the slope of my tangent line appears to be about 2. I can also approach from the right, and I can take values like 2 or 1.5 or 1.1, and I can look at the secant lines for those values, and something very similar is going to happen. So I'm just going to do this using the table. If I use the value of x equal 1.5, then and I calculate the corresponding point and slope, and if I use an x value of 1.1 and I calculate the point and the slope, the corresponding slope will be 2.1. And if I use the x value 1.01 and I calculate, I will get the secant line will have slope 2.01. So you can see from either, whether I choose points that are on the left, to the left of 1, or I choose points to the right of 1, either way, the slopes appear to be approaching, the slopes of the secant line are approaching 2. So what we can write to summarize what we've discovered is that the limit as the point Q approaches P of the slopes of the secant lines is equal to 2. Or, in other words, the limit as x approaches 1 of this quantity, x squared minus 1 over x minus 1, is equal to 2. And so I want to be clear that this was the slope of the secant lines, right? And this is what I originally called MPQ, and that this is what we are going to define to be the slope of the tangent line. So it is that limiting value. Okay, and as a result, what I'm going to write is that so since the slope of the tangent line is 2, and since it passes through the point we can use the point slope form of a line to get an equation of that tangent line. So this would be y minus 1 is equal to 2 times x minus 1. Okay, so this is the slope, this is the equation of the tangent line.